Hello everyone and welcome to this talk of filter list generation for underserved regions. My name is Alexander and I'm from Chalmers University of Technology in Gothenburg, Sweden. This is joint work with Peter Snyder from Brave Software, Antonio Pastor from UC3M in Madrid, Panos Papadopoulos from Brave Software and Benjamin Livshits from Brave Software and Imperial College London. The outline of this talk is that I will first motivate the need for filter lists in underserved regions. I will then talk about a browser instrumentation which allows recording the execution of the web page as a graph. Then I will talk about a hybrid classifier for classifying ads. I will then talk about how the browser instrumentation and the classifier can be combined to generate filter lists. And lastly, I will show an evaluation of 3 underserved regions using this technique. So to motivate this a bit, if I go to one of the biggest newspapers in Sweden, I see several ads, which I have marked with a red border on this slide. And fortunately for me, I can also use tools to make them go away. And for instance, an ad blocker. And the thing that these tools build upon are filter lists, which are the unsung heroes of content blocking. So filter lists, they can help reduce data use, which can be important if you're on a metered connection or if you're on a mobile device which is not connected to the Wi-Fi but on a mobile network instead. It can help protect users from malware, where some ads have been known to serve malware as well. It can help improve the browser performance, and not just by, say, faster rendering because less resources are being loaded, but also a better user experience when browsing the web. And it can help reduce tracking, which of course is good from a privacy perspective. And the way to do this is that you have a filter list with known trackers. And if you want to use this, you can use either a browser extension such as Adblock, Disconnect or uBlock, or you can use a full-fledged browser which have this built in already, such as Brave. So these filter lists, well, the most popular ones are EasyList for ads and EasyPrivacy for trackers. And generating these lists, it's a crowdsourced effort. And these most popular filter lists, they target global sites, which are sites in English, but resources which are popular enough to also appear on English web pages will of course also be blocked. And the case, for instance, for the Swedish newspaper is that those resources are blocked just by running EasyList. But what if you are visiting a non-English site which use not very popular resources? Well, this is a screenshot from an Albanian site which is browsed with EasyList enabled. And as you can see, there are still plenty of ads around there. So what can be done in this case? Well, for that, we should use supplementary lists for the different regions. And EasyList have 16 supplementary list subscriptions available. But if we go to filterlists.com, which is just a collection of a lot of filter lists, here I've sorted them to show the ones that have an Adblock Plus syntax, which is 325 lists. Some of them are just a regional list combined with EasyList, and others are for very specific regions. Some are for very specific kind of resources, whereas others are more general. And unfortunately, not all regions have a filter list, but even if they have a regional filter list, they might not be well maintained. And the existing prior work on automating filter list generation, it's focused a lot on the global lists, either by replicating them to show that their generated list is just as good, or extending them. And we've seen little to no evaluation or applicability to non-English web regions. And our goal in this work is to help improve filter lists for smaller non-English regions. And to do this, we create a 2-stage pipeline, which consists of a deep browser instrumentation, which I will talk about next, and a hybrid ad classifier to help determine whether or not a resource is an ad. So that concludes the motivation section, and I will now talk about the browser instrumentation, which we call PageGraph. So PageGraph allows us to record the web page execution as a directed graph. And this allows us to attribute every page modification and network request to its actual cause, which is usually a JavaScript unit. Nodes in the graph, they are elements in the web page, and edges are the interaction between the elements in the web page. And all page behaviors in the top level frame and the child local frames will be captured in PageGraph. It consists of a large set of patches and modifications to the renderer Blink and the JavaScript engine V8. In total, it's around 12,000 lines of code. And this recorded graph is available both online, directly in the browser for immediate inspection, but we also export it to a GraphML file for offline analysis. And this graph representation, it makes it easy to determine if an image was injected in the page by a script and how that specific script came to be in the page, and so on. So you get like a full causal chain of any specific resource, how it ended up on the web page. And I will now give you guys an example to hopefully give some intuition of how PageGraph would work. So imagine we have this script tag. It consists of creating an image element, setting the source attribute to it, and appending it to the DOM. Now, within the browser, first the HTML parser will see that, well, I need to create a script element. And this script tag, it consists of text that I need to create, and I need to append it. And in order to execute this, we also need to compile this script element. And all of this is targeted, tracked by PageGraph. But now, once it's compiled, we can start the execution of the script. So the first line, we create an image element, which means that we will add a new node to PageGraph with an edge from this JS script that says create. On the next line, we set the source attribute, which means that, again, this JS script will have a new edge going to the image element that says that we set the attribute and also which attribute we set. This, in the browser, will make a request take place from the image element to the actual resource. And in PageGraph, this corresponds to a new node, which corresponds to the resource, with an edge from the image element to the resource saying that the request is started. On the final line, we append this image element to the DOM, which means that we insert it. So we add an edge from the script to the image element that says that, well, the node has now been inserted. And once the resource is fetched, we will generate an edge that says that the request is completed. And all of the edges in PageGraph, they have a timestamp, which makes it easy to see the exact order of execution. And that concludes the browser instrumentation. And next I will talk about the hybrid classifier. So at first we wanted to have a purely perceptual classifier, but it didn't generalize well enough. So we used the ideas from Zainul Abidin et al. In their paper about Percival, which is a perceptual ad blocking with deep learning. We expanded the SqueezeNet-based CNN used in Percival to a ResNet 18 network instead, because we could take the extra performance hit because we were not going to run this in browser. In the table, the original training data row, that was the data that was given by the Percival authors, as well as some data by us. But we also needed the generated graphs for this work. So we also collected some new training data once PageGraph was up and running. And when we applied that to the classifier, we could see that the accuracy dropped significantly and the precision dropped significantly, which made us question whether or not this would be good generalization across languages, because it didn't generalize particularly well within the same language. So we decided to add some contextual features. And these contextual features could be extracted from the page graph that we got. In total, we add 29 features, such as: is the resource URL a first or a third-party URL? Is it injected by a script? What's the node degree for the parent? What's the node degree for the current node? What's the dimensions of the image? What's the length of the resource URL? And within these 29 features, the perceptual classifier's add probability is one of the features for the hybrid classifier. And as we can see, the recall dropped to 75%, but both accuracy and precision went back up. So we had a classifier that we were reasonably happy with. So that concludes the hybrid classifier part, and I will now talk about how PageGraph and the hybrid classifier can be used to generate filter lists. So if you recall, I mentioned request chains before, which is just the full chain of requests that makes a specific resource appear in the DOM or on the web page rather. And in this case, let's say that we have an add image. We know we want to block the add image, but as we can see here, we have 3 different places to block. We can either just block the image, or we can block script 2, or we can block script 1. So the question is, which one do we actually want to block? And in order to determine that, we want to break the page as little as possible. So we need to determine some safe blocking in these request chains. And we do that with a simple heuristic. So we start with the identified add resource, and if it's a script and the script creates more than 2 subtrees in the document, then we stop. That script is not safe to block. And if it's a script that inserts another script which matches the previous condition, then we stop, because that's not safe to block. Otherwise, we block and we continue upwards in the chain. So in short, it basically means that a script that does no modifications to the structure of a page is safe to block, and a script that makes modifications which are isolated to 1 or 2 parts of the page is safe to block. So with this in mind, we can go back to the request chain, and we want to block the add image. It's not a script, so it's safe to block. It's not creating any subtrees. So then we move back 1 step in the request chain. So we come to script 2. And script 2, it creates 2 subtrees. One of the subtrees will be removed because that's just the add image subtree. So script 2 is also safe to block. So then we can mark it safe to block, and we move back to script 1. Script 1 in total, it inserts a script tag, an image tag, a div tag, and script 2. So it creates 4 subtrees in the DOM. One of them will be removed by blocking, but it still creates 3 additional subtrees. So script 1 is not safe to block, which means that we determine that the best place to block will be here. And both script 2 and add image, we can get the resource URL from those resources that will be blocked, and we can use them to then generate filter list rules. So how do we generate the filter list rules? Well, let's say that we start with this example, right? And the first thing we do is that we want to reduce the URL's domain to its effective top-level domain plus 1 root, which means that a.good.example.com will just become example.com. The next thing we want to do is that we want to remove the query parameter portion of the URL. So in this case, the question mark ID equals 3 will be removed. Because the query parameter part, it can contain irrelevant tracking information and other things like that. So to make it more general, we want to remove it. Next, we remove the fragment portion of the URL. So this hash anchor will disappear. And we don't just want to block this on HTTPS, we also want to block it on, say, HTTP. So we remove the protocol from the URL. And then we convert this to a right-rooted adblock plus format filter rule, like so. And this approach, it's designed to generalize, for instance, other similar requests, even when irrelevant details like tracking related query parameters might change, so that they will all be blocked, but not so much so that unrelated materials served on the same host will be blocked. That's the main idea of generating the rules in this way. So with that, I conclude the filter list generation part of the talk, and I will now talk about the evaluation that we did on 3 underserved regions. So the first thing that we had to do was that we had to select which regions we were going to use for evaluation. And we set up some criteria for it. One was that the language should not be a major world language, because if it's a major world language, most likely you have good enough supplementary filter lists. There should exist at least one supplementary filter list for the region, so we had something to compare against. The updates to regional supplementary lists should be significantly lower compared to more popular lists, which means that the activity of maintaining the supplementary lists should be less than for the popular ones. There should be a vast increase of internet usage in the past decade, and with this we basically mean that we should see a significant rise of the population that got access to the internet in the past decade. It should have a popular sites listing on Alexa top sites, because we want to crawl regional specific web pages. And we should be able to purchase or access a VPN with an exit point in the country, because if we don't have that, we will not be served the ads as if we are within the region, which is the main goal of this crawl. So with this in mind, we selected 3 regions, Albania, Hungary, and Sri Lanka. And just to compare their regional filter lists, we can first look at the total commits between 3 more popular lists, which are India, Germany, and Japan. And we can see that the amount of commits differ significantly, in particular for Albania and Sri Lanka. But total commits, it doesn't tell the whole story, because it can be a reasonably new Git repo for the list. So then instead, we looked at the commits per month, basically from the start of the Git repo. And again, Albania and Sri Lanka had 0.27 and 0.35 commits per month, which means that their supplementary lists are not maintained at all, basically. For Hungary, we had almost 9 commits per month, which is still, well, it's 1 commit every 3-ish days, but it's still significantly lower compared to the more popular ones. Japan had almost 25 commits a month, India had about 82 commits a month, and Germany about 166 commits a month. And these are the lists that we found through filterlists.com. So how can we actually evaluate this then? Well, first off, we crawl the Alexa top 1000 for each region with PageGraph. And we went to the landing page and 2 child pages. So that means up to 3,000 pages in total. And we stay on each page for 30 seconds to allow all frames to load. And then we save all the requested images. We screenshot all the frames after those 30 seconds. And then we classify all the images and the frames with our classifier. And we also find the resources that would be blocked by the current lists, which in this case are the combined EasyList, EasyPrivacy, and the regional supplementary list. Then we generate the request chains and find the best place to block for all the resources that either our classifier or the current lists would say that should be blocked. And based on this, we then generate some filter list rules. And if we just look at the unique resources found, in Albania we found the current lists would block 2,850 unique resources. our classifier found an additional 460 resources, which combined with the chains got up to 511 additional unique resources to be blocked, which is an increase of 18% for Albania. For Hungary, the current lists would block 1,819 unique resources. Applying this to our chain methodology and the classifier, we find an additional 586 unique resources to be blocked, which is an increase of 32.2%. For Sri Lanka, we had 1,872 unique resources blocked by the current lists, which applied with our classifier and the request chains got up to an additional 674 unique resources, which is an increase of 36%. So in total, across these three regions, the current lists would block 6,541 unique resources. We find an additional 1,771 unique resources with our classifier and the request chains, which means an increase of 27.1% of new unique blockable ad resources for those specific regions. So, to conclude, I have presented a novel approach for generating filter lists for underserved regions. It's based on deep browser instrumentation, which helps generate a graph over the page execution, and also a hybrid classifier, which consists of both contextual and perceptual features. We've applied this to three underserved regions, which is Albania, Hungary, and Sri Lanka, and in total we generate 1,310 new filter list rules. We identify 27.1% extra unique resources to be blocked, and the overall blocking across these regions improved by 30.1%. And everything we've done here is open source. If you want to check out PageGraph or the filter lists or the code for generating them, you can just go to the Git repositories or the Google sites. And if you have any questions, I'm more than happy to answer them. And if you want to contact me, my email address is at the very bottom of this slide. So with that, I say thank you very much, and I hope you all have a good day.